So,
okay.
Yeah, so in this session we have 5 speakers, 4 online and 1 offline. So first off is from Dr. Lokesh Dewangan from PRL. So he will be talking about why the massive stars, how they form. So Lokesh, because we have very short time, so we only 25 minutes here. So
inner circumstantial environment of the O-type star. So more details of this I will talk in my later slides. So these are the list of my collaborators and my students. So in this presentation, I will focus on the following points. Starting, I will give you some brief of these massive stars and their impact. And then I will talk about the comparison between the low mass star, massive stars, and what are the problems in study the formation of massive stars. Then later I will talk about where we can actually look for this massive star and we try to understand their formation process and how we study their formation of massive stars. So I will present some of the results and finally I will summarize the results at the end. So in general, we know all the stars form in the molecular cloud. So gravity is one of the principal source for this formation of stars. So if you look at any molecular clouds, you have a different components. Like molecular cloud is a bigger component. Then you have a filamentary structure, clump. Then you have a core, and then you have a young stellar sources or infrared access sources within those cores. So some typical parameters of these different entities are listed here. In general, we can also classify this star based on their masses. So sometimes we can say this is a low mass star, intermediate mass star, or massive star. That we basically decides based on their masses in terms of the solar mass. So when we say massive stars, so we refer the stars having the masses more than 8 solar masses. And below this 8 solar masses, they are called low mass star, intermediate mass star. Now, if you look at this molecular cloud at different wavelengths, like suppose you look at this sky in mid-infrared. If you look at this, star forming regions in mid-infrared, you have bubble-like features, which is shown here. So this is some typical example of the bubbles. You see the nice boundary of this like bubble-like structure, and inside this bubble, you have a radio continuum emission. So you have an ionized emission inside these bubbles. So if you look at the same sky in a longer wavelength, let's say 200 micron larger than images, so you will find so many filamentary-like features. How do you define filament? So you have let's say robe-like structure. You have a length divided by its width, so that gives you the aspect ratio. So the filamentary features are known for the higher aspect ratios, and also these filamentary features are found in a different morphologies. So one is this linear morphology. Then you have there is a dense region. Then that dense region is surrounded by several filamentary features. Those called half filamentary features. So I'll come back in this kind of configuration in later my talk. So these are the very important components in our in molecular clouds. So in general, if you can divide this low mass star or a massive star in terms of this filamentary association, so elongated filaments mostly they harbor this radially this low mass star forming cores. But if you go for you have a dense region and surrounded by several filamentary features, those hub-like filamentary features, they are appropriate regions for these massive stars. So now, what are the signatures of star formation which we know? So in general, we know these star forming regions are associated with the outflows. They have infall signatures. Also, you find, as I said, bubbles like features are there. Then they are associated with the radio continuum emission, the ionized emissions. They are also associated with the masers. Then young stellar sources are infrared access sources. Then you have a hard molecular cores. They are simple cores, but they are associated with the complex organic molecules. And also, if you measure their temperature, they are very, very high, more than 100 kelvins. So these are the cores are known as a hard cores. So suppose you have any star forming regions and this kind of signature, so they are known as a protostellar activities that are going on. Suppose you are studying a core where you don't find this kind of signature, so they are called pre-stellar cores. So remember this pre-stellar cores and protostellar cores that will be used in my later slides. So these are some examples of outflows and jets and bubbles and these filamentary features. So what we know from the low mass stars, as I said, low mass star means you go for 0.8 to 2 solar mass. They are called low mass stars. So these sources are known they are most abundant basically, these sources, and they are formed through the accretion process. What is the accretion process? So you have a central protostar which gains the mass through the envelope and the disc-like structure. So this, in accretion process, you have a signature of outflows and infalls. So these are the process which is very well established for the low mass star formation. So the signatures of accretion is the outflow, jets, and accretion disk. So here I am presenting one of the disc-like structure of nearby low mass star forming region, that is the HL tau. This image is taken from this ALMA observatory, ALMA image. So you nicely see there is a protostar and surrounded by disc-like structure. So this is the signature of the accretion process. So now I will talk about little more about this massive star. So as we know, if you go for higher masses, so if mass increases, you have a luminosity, higher luminosity. So these massive stars, they are significant. So they have a significant impact on the evolution of galaxies and universe in general through their energetics. So these are the sources which have a higher luminosity. So we can also classify these sources into different, B-type, O-type stars depending on their masses. And so these sources are, source of jets, winds. They have a ultraviolet radiation. So this massive stars emits very copious amount of ultraviolet photons, which suppose this energy exceeds 13.6 electron volts. So they ionize their surroundings. And because of this, there is a recombination and there is ionization. So if you equilibrate between this, so you form the H2 region. So these are the sources responsible for the H2 region. And also when these sources evolve at their later phases, so they explode as a supernova. When they explode as a supernova, they actually enrich the heavier elements to the surroundings, and also their remnants can be a black hole or can be neutron star, that depending on their masses. So these are the very, very important. And additionally, these sources are, they expand to their surroundings. So they have a negative impact and a positive impact in their surroundings. So they can trigger a new generation of star formation. So despite their importance, their mass formation processes are not very, very clear. So what are the regions behind those, study of the formation of massive stars? So what we know from low mass star, let's see. So the accretion, we can calculate these two kinds of, time scales related to their formation of star. One is the accretion time scale, another is the thermal time scale or Kelvin-Helmholtz time scale. So this Kelvin-Helmholtz time scale is basically how quickly a star would collapse in the absence of nuclear energy. So if you measure this time scale for massive star and low mass star, you will find those calculations. They will show that the massive ones have a very relatively very low this time scale for the low mass massive star. But if you go for the low mass star like sun-like stars, so they are like 10 million years. So this you can just compare. You will find that this TKH is very, very small for the massive ones. And similarly, if you compare with this accretion time scale, so for the low mass stars, this Kelvin-Helmholtz time scale is higher than this accretion time scale. And in the case of massive star, it's just opposite. So the accretion time scale is higher than the thermal time scale for the massive one. So what it means that? So it means that the massive star form is still in the accretion phase. They reach to the main sequence and still accrete the materials. So this is one of the most important thing. And as I said, this massive star has a high luminosity. So high luminosity means high radiation pressure. So suppose you apply this low mass accretion process, which we know that suppose you apply for this massive star, what will happen? Suppose this low mass star accrete the metal and becomes 7 solar mass or 8 solar mass. Then once it reaches to the 8 solar masses, the luminosity will be very high. So the radiation pressure will be very high. So in that case, what will happen? Surrounding material will be destroyed by this tremendous radiation pressure. So suppose you don't have material, then how this massive star will gain the mass? So how will become a very O-type star or more further, massive one? So this is the problem. But in general, we have massive star in our universe, in our galaxies. So what are the processes which basically responsible for their formation? So and additionally, what are the challenges we have to study this massive stars? These massive stars are typically very, very far away, except this Orion Nebula. So this Orion Nebula, they are located at very nearby, like 450 parsec. But if you look at other star forming regions, they are typically located at 1 kiloparsec or more distant. And they are very rare because their time scales involved in these sources are very, very small. So they evolve very fast. So if they evolve very fast, then it's very difficult to catch their critical early phases. Why we need to study to explore the critical early phases? Because these are the phases sources where you have a initial condition where this massive star is formed. But if you go for low mass star, you can catch any early phases of low mass stars very easily. But in the case of massive star, is one of the difficulties. Then these sources are deeply embedded in their dusty clumps, so they suffer high extinction. Extinction is a absorption and scattering of light from the dust, and these regions are deeply embedded in their dense clusters. So there is a when you have a massive star, you find that cluster low mass star surrounded by this massive star. So you have a confusion to pinpoint which is the your massive star. So these are the observational challenges. So in order to explain this formation of massive star, what are the theories available in the literature? So we can divide these theories based on two major categories. One is the core fed scenario, another is a clump fed scenario. So this core fed scenario is one of the flavor is a turbulent core model. So this model says is similar to this like scale-up version of low mass stars. So we know the low mass stars form through the accretion process. But low mass in the case of low mass star, the accretion rate is 10 to the power minus 6 and 10 to the power minus 7 solar mass per year. But suppose your accretion rate, if you increase the accretion rate like 10 to the power minus 3 solar mass per year, then what will happen? So this radiation pressure will be overcome by this RAM pressure. So this is the important ingredient of this model. But this model says you need a single isolated massive pre-stellar core. Remember, pre-stellar core. So before any signature of star formation activity, you should have a very massive core, single isolated core, which will eventually form a massive star. So this is one of the important signature of this scenario. And you need, so basically observationally, you can find accretion disk and outflow in this scenario. But still researchers are looking for massive pre-stellar cores. So this is very, very difficult task. So far we have not very much samples of this massive pre-stellar cores which support this scenario. And also accretion disk around very massive star like O-type star. This is a rare phenomena which people have not observed. So now there is another theory is the clump fed scenario. So in the clump fed scenario, you have a different flavors like competitive accretion, inertia inflow models, and global hierarchical collapse. So these are models. What is the major theme about this scenario is that you have a large scale cloud, then you go towards the clump and core. So this core gets material from the large scale to the smaller scale in that scenario. So what is the main assumption of this scenario is that the massive stars are born with the low stellar masses. So these low stellar masses gain the mass from their large scale environment to the core scale. So this is the one of the important point of this clump fed scenario. So now now there is a three flavors I told, that competitive accretion, inertial inflow, and the GSC. So the way accretion accumulating material happens, so the driver of mass accumulation, the mass flows, is a different if you go for inertial inflow or GSC. So this is only different, but overall the scenario is that you have a large scale environment from where you get this low mass star gets the material from their surrounding large scale environment. So this is the theme of that. So in nowadays people are getting more and more signatures related to this hub filament system, as I mentioned in my introduction slide. So in those configuration, people are getting this accretion through the filaments. This is very close to this clump fed scenario which I just discussed. So this is also called hub filament system. So what is the hub filament system is? So you have a central core which has a higher column density, order of 10 to the power 22 per centimeter cube square, and then you have a surrounding filamentary feature which has a higher aspect ratio but low column density. So this configuration are called hub filament configuration. So here, this is a typical example of hub filament configuration. So in the central part, you expect the massive star, also low mass star, and cluster of low mass stars. So what you expect also, the material should inflow from large scale through filamentary feature to the central one. This is a central hub. So this is the accretion through filaments. So this is related to the clump fed scenario. So in based on this scenario, people have given a evolutionary model sequences about this. If you are interested, you can go for these references. So what they say, you don't have actually high mass pre-stellar core. Remember, again, I am mentioning that pre-stellar, massive pre-stellar core, you don't exist in this model. They suggest that you don't expect this, but you expect low mass pre-stellar, that even that becomes protostellar, low mass protostellar, that gain the mass from their surrounding large scale surroundings, and then eventually that become massive one. So this is the scenario which people have presented based on this presence of hub filament configuration. And this is, so you can also, this is GSC scenario, that stars, core and ridges, means those filament configuration, they simultaneously grow the mass from their parental cloud. So this is the main assumption of this theory. So in order to study this massive star formation observationally, what we need? So we need a multi-wavelength data. So we need an electromagnetic spectrum. So as I said, the stars form in the molecular cloud. So these stars are deeply embedded. So you need a longer wavelength data which penetrate inside their dust cocoon. So that's why you need a longer wavelength data to study these sources. So in order to study this, star forming regions or massive star forming sites, you need to study there where you need to trace the different components, like where is the ionized components, where is the molecular gas, where is the dust emission, so where is the YSOs, so where is the YSOs stand for Youngster object. So you need to trace those sources. So we need multi-scale and multi-wavelength data to study these sites. So and also we use this line data. So as you know that, right? We have a continuum data and we have a line data. So in continuum data only you have a 2D images, but in the line data you have information, additional information. This is the velocity. So you have a area and you have a velocity information. So you can study their gas motion along particular direction along the line of sight. So in general, what we do, we look for the spectra along our target site and then we integrate. That gives you the moment zero map. And so also we generate the moment one map that gives you the information of this velocity at each pixel. And also you can produce the moment two map that gives you the velocity dispersion map. So each pixel you have a velocity velocity dispersion information. So this please keep this information in mind, because later I'm going to use this in my to present some of the results. So what are the location where we should study the massive stars? So the massive star forming regions contain filaments, mid-infrared bubbles, H2 regions, 6.7 gigahertz methanol measure. Remember this, I will come back. This 6.7 gigahertz methanol measure and Youngster cluster. So why I'm giving more emphasis on this 6.7 gigahertz methanol measure? Because these kind of measures exclusively found with the massive stars. They are not detected with the low mass stars. So if you detect this 6.7 gigahertz MME methanol measure emission, so there is a probability that you are actually tracing the younger massive stars there. So these methanol measures, the 6 MME, can be associated with the ionized emission and may not be associated with the ionized emission. So if you have this absence or presence of ionized emission, you may detect the very earliest phase of massive stars. So this, if you want to know a little bit of the measure, so this is similar to what we know in the laser. So L stand, light amplification. Here is the measure stand for microwave, and the same rest is the same. So this measure can be found as a class 1 and class 2, but we are exclusively give attention to this class 2 6.7 gigahertz methanol measure. These are non-thermal sources. So in this talk, I am going to present one of very interesting results related to this W42 site, where actually I have explored very large scale to very, very small. Large scale means several parsec scale to several hundreds of AU scale. So, and here we have identified very early phases of massive stars. So how it looks. So if you look at the left side, this is a mid-infrared color composite map. So this is the special view of this W42 region. So this is RGB. You can see the color code here, and this the location. This star symbol locates the location of O-type star, which people have earlier reported. And if you look at the same field of view in the Spitzer longer wavelength sub-millimeter images, This is the color composite map of the Herschel, submillimeter, three different images. You see the comparison. So here you look at this mid-infrared, you have a dark features like elongated features here, and this is saturated central region in the 24 micron. And if you look at this here, you see you can compare nicely. This is the emission feature. So here is the bubble like bipolar like nebula is here, but if you look at this submillimeter, you have a elongated filamentary features. And this source is located at the 3.8 kiloparsec. And this is the size of this area which I have presented here. And as I said, this is a 2D, is a 2D image. Now you want to study the molecular cloud. So in star formation, I mentioned we study the cloud, clump, core. So now this you have seen this submillimeter images. Here you look at this is the molecular cloud, the gas distribution of molecular gas related to this W40. So you nicely see this filamentary feature in the molecular map. So this is this cloud is studied at traced at the 58 to 70 kilometer per second, and the resolution of this image is 46. So you can't see inside this cloud. So again, I'm showing you the center region using this Herschel 250 micron. What you see there is you can easily compare here. This is a central region which I have presented here. So this is and also I marked some hand filamentary feature which is seen here. Here you can see nicely there is a star symbol which represent the location of O star, and there is a diamond symbol that represents the location of 6.7 gigahertz methanol measure, MME. Now I'll use this word MME in my next remaining slides. So this is here you can see the O star and MME location. Now you zoom this is 250, again I am showing 350. You can nicely see the center region zoomed in here. You see this center region and surrounded by these filamentary like features. So this sort of half filament configuration, you have a center region where you can see very dense material, and then filamentary like features which having a high aspect ratio. So this can be referred as a half filament configuration. Now if you look at this center region, there is also I have overlaid this GPS 6 centimeter continuum contours. So this is the RG map using this Sophia 37 micron and 25 micron image RG, and overlaid this 6 centimeter continuum emission. So this is the star symbol which locates the O-type star, and this is the methanol measure. So here you can see the point-like sources even in 25 micron. So that can be referred as a infrared counterpart of methanol measure, MME. So here I refer is a W42 MME because it's a counterpart of this methanol measure. And also you don't see much significant radio continuum emission here. Now here this is the left side is the H2 image. This is a continuum subtracted molecular hydrogen. So this is the location of star symbol, as I said, this is the location of O star, and this MME location traced by this diamond symbol. Now you nicely see this elongated emission. This is the H2 molecular hydrogen. So this is the outflow activity. So you see the outflow, parsec scale outflow structure here, and this is the location of methanol measure. You see there it looks like that. This is the driving source is located here, which drives this parsec scale. Now look at the same field of view in the 8 micron image. So this is the location of MME, and you see the point-like sources here. If you do the modeling, spectral energy distribution of this source, we derive the mass of almost 20 solar mass, and the luminosity is 4.5 into 10 to the power 4 solar sun times solar sun.
Lokesh, you have 5 more minutes.
Okay, so here now look at this this small box. I'm going to zoom this. So far we have seen the large scale. Now we are going to see the very small scale environment of this O-type stars. So this is the adoptive of this 8-meter class telescope using this K-band, and now you can see this area has been zoomed. Please note that this area has been zoomed here using the K-band, and corresponding you have a 3.8 micron. So in K-band you don't see much, just diffuse emission you see, but you see as you go for the 3.8 micron, you see the point-like source and this envelope structure, and also you see the diffuse emission. If you see this, with respect to this point-like source, if you go and measure the distance, and also you go the south, you have a almost similar distance diffuse emission are seen with respect to these point sources. And so far we have seen only continuum data. Now I just combine this outflow, H2 outflow with respect to this small scale. This is the RGB, just using this K band and L band images in RG. You see the center region, and this is the outflow activity. So this source is that this circle that represents this position of massive star, that now it looks like it driving the outflow. So in order to study the gas motion and the high resolution, clump morphology or core morphology of this source, we have used this ALMA observation, and these are the different lines which trace the soft gas, outflow, and dense gas. So we use this, and so this is ALMA one. This is the archival data is 1.3 micron. You see nicely there is a core associated with this methanol measure, W42 MME, and other clumps. So in order to see further what is inside that, we have used our own ALMA high resolution 0.3 arcsecond continuum image, and we further resolve this. You can nicely see these structures in the continuum. And again, I am showing you, I have zoomed in this, this is the slide which I showed you. This is the image I showed you in the first slide. So this is the continuum image. And I'm going to zoom this image in the right side. You see this zoomed in image. This is the L band image. Background is a 3.8 micron image overlaid with this ALMA continuum emission. So you see there is a point-like sources in the L band. This source is nicely traced with this ALMA core. This is the core A. And also you look at nicely, there is an envelope-like structure, and also there is a B, C, D like point-like sources surrounded by this A-type structure. And also we have identified the outflow, molecular outflow using the CO with this velocity. And there is a nice outflow is traced by this drives by this source. And also if you look at the north, you see there is an outflow, material is there, soaked gas is there. So the background is H2 image, and overlaid this molecular, and also this is the line data. This is S13CO plus. So we can also use the other lines and determine the temperature of the core, and we found that there is this really is a hot core. And in order to study, the gas at the different lines with different density gas tracers. So we have shown here, you see there is a continuum, and this is the S13CO plus emission and this SCO plus emission. Mind it, we are not talking about almost 1000 AU scale around the massive O stars. So we have seen the large scale. Now I am going deeper and very inside the O type stars. So here further some other different line emission is overlaid on this NACO infrared images. You see this CS3OH, SiO, then nitrogen sulfide, then you have a CO and CS3CH and CO outflow. You can nicely compare that. So this is the one of the important results which we have found. This is the RGB map using your red, this is a 3.8 micron image, which and green, and green is your 13 CO plus emission. Sorry?
Lokesh, only 1 minute. Yes.
Okay, yeah. So this, now you see this, point-like sources, and this, you see this flattened-like features. So these flattened-like features, and also we overlap the outflow. So now you see this flattened-like feature is almost perpendicular to this point-like sources, and the outflow is also going perpendicular to this flattened-like feature. And if you look at the other, tracers and their velocity, this is a moment one map. If you look at the moment one map, the velocity structure, so you find a significant velocity gradient. So this allows us, there is a disc-like features exist around these sources. So these results we have highlighted in Nature in India. And the most important thing is that the core forming massive protostar does not accumulate all the mass before the core collapse. What I mean, so the core, you can calculate the mass of the core which hosting this massive star, that is low mass. That is not very, very massive one. So the low mass star, the low mass core basically forming very massive stars. So this is the results we have found, and some results related to half filament system we have published. And these are the some regions. Because of this limited time, I'm not going into the details. So the most important points in the talk is the understanding what physical processes determine the mass of a star is an active area of astrophysics. So several key questions in high mass star forming focus on the early fragmentation of prestellar massive clumps. Do high mass prestellar cores exist early on? it is difficult to identify pre-stellar massive clump candidates that can form massive stars. So searching for the massive pre-stellar core is an open research topic. So what is the take-home message from this talk is that examples concerning the role of filaments, this accretion through filaments, are steadily increasing. The infrared bright massive protostar grow from their low mass sources, which gain the material through gravitational or supersonic driven inflows from the parental molecular massive dense core clumps. So this process is very promising to explain the formation of massive star and provide important clues for understanding of the process of mass accumulation in massive star formation. That is the one of the challenging in massive star formation is the what is the mass accumulation process. So with these results, I conclude here and thank you very much for your attention.
Yeah, thanks Lokesh for the nice talk. So now we are open for question and answer. So any queries from audience here?
Hi, thank you for the wonderful talk. So I had two questions. One of them was about the formation of neutron stars and magnetars. We think that magnetars are somehow formed differently from neutron stars. We don't know what process leads to the formation of magnetars. But is it possible that in this hub and filament formation scenario, some stars get a very high angular momentum, for example, which leads to a generation of a higher magnetic field in the supernova or something of that sort?
I need to check this because you are talking about evolved stage of those supernova explosion related things. So I need to check this.
Okay, sure. The other question I had was if you have any plans with JWST for observing these, because it will be able to give you a very high resolution view of these stellar clusters. So can you say what you're hoping to learn from, what the community can learn from JWST?
Yeah, definitely. Yeah, we need to go for the high resolution images in mid-infrared. And also, if you get a spectroscopy observation toward these sources, you can study the ionized flow, gas ionized flow, and also the well structure of the H2 emission, because those give you those observations give you line observation, spectroscopic observation. So you can do those information, extract those information from these kind of sources. That will be really helpful. Thank you.
There is a hand raised by Arpita, right? Arpita, please go ahead.
Yeah, hi Lokesh, very nice talk. Actually, I have two quick queries. One is like, is it possible from your observations to comment on the typical rotation rates of these massive stars as soon as they enter the main sequence? And the second one is like, can you comment anything on the core mass functions?
First, related to the rotation, we have not tried. We have to look for that.
Mm-hmm. But is it possible from your observation?
It is possible. We can try that. Yeah, you can examine the rotation, core rotation. That is possible. And related to the initial mass function, we need a distribution of masses. We need a distribution of masses. So here I am just concentrating on one source, one core. So you need a large number of cores. So there are groups who are using this ALMA data for different stuff, massive stuff on regions, and they are trying that.
Yeah, exactly. So that's what I was thinking, like, as right now another person mentioned about the JWST and combined effect of ALMA. Is it possible to comment on the CMF as well?
Yeah, that will be wonderful, because in this source I have shown you the adaptive optics near infrared image, and then we have gone for sub-millimeter. So the near infrared images gives you the location of point sources. But that is not possible in the longer wavelength. That only you can see the core and clumps or accretion disk, but you can't see the location of protostar. So that is the beauty of in my work we trace the location of protostar and we found the flattened disk-like structure. That's why we are able to connect those things. So that's why we are saying there is a disk-like structure is there around those massive protostars.
Yeah. Okay.
So
thanks.
You need complete spectrum to go.
Okay. Thanks.
Yeah. Thanks, Lokesh. Yeah.
Thanks, Lokesh, for a very nice talk. Our next speaker is Arpan Ghosh. His title of his talk is Gaia 20 EAE. a newly discovered episodically accreting young stars. So Arpan, can you share your screen? Lokesh, you have to unshare your screen.
Okay. Thank you. Thank you very much.
Yeah, Arpan, you please go ahead and share.
Hello, am I audible?
Yes.
Yeah, okay. I'm sharing my screen.
So Arpan, please try to wind up your talk in 12 minutes because we are already running late.
Yeah, is the screen visible?
Yes, please go.
Yeah, okay. I'm the topic of my present talk is Gaia 20 EAE, which is a newly discovered episodically accreting star. I thank the ASI 2020 SOC for giving opportunity to present this talk. So this is what you can see, the 3.6 meter dot, and is the 10 spec, and this is the K-band image of this Gaia 20 EE obtained on October 2021. So here you can briefly see, this is the present outline of my talk. I will give a brief introduction about what is episodic accretion, and then about this Gaia 20 EE, its location, the distance, and our observation and the findings, and finally I will conclude in the discussion section. So what is episodic accretion? Episodic accretion is the sudden enhancement of the accretion rate in the pre-main sequence low mass young stars from the circumstellar disk because of the, it arises because of the various instabilities that arise from the disk. So this phenomenon was first observed in 1936 when the first prototype of this category of sources, FEORI, had a major eruption of around 6 magnitude in the V band. So from 1930, and it was only in 1966 when G.H. Herwig first realized that it represents one of the important stages of the low mass star formation. Alongside, you can see the cartoon image of this kind of sources and the different parts of the electromagnetic spectra which we use to probe the different parts of these objects. So in the grand scheme of this star formation, this is the low mass star formation where this kind of sources are found. These sources, so this is the isolated star formation paradigm where in the class 0 stages, the molecular cloud collapses to form the dense core in the center, and then in the class 1-2 stage there is this remnant infalling envelope, and then there is this circumstellar envelope, and then the central star, and then class 2 or 3 stage when the envelope disperses and we only have the disk, to the class 4 stages when even the disk also disperses. So in this paradigm we find this episodic accretion mainly in this class 1-2 stages where still there is the remnant envelopes are there, and as more and more this kind of sources were developed, as you can see, this based on the outburst amplitude and also the duration of their outburst, they were categorized into 2 broad classes. Those which exhibited the outburst in the like that of FEORI are termed as FEORs, like V1057 Cygnus or V1515, which had a long outburst and both in the terms of magnitude and the duration, and their weaker cousins named after X Lupi, which are called XORs, which had smaller outburst rate and also multiple outbursts. So this is the broad classical definition of this category of sources. Now I will be talking about the Gaia 20 EAE, which we have been studied extensively. So it is located in the W51 star forming complex, and you can see the coordinates of these sources. So it is located in the W51 star forming complex. There are 2 molecular clouds, MC1 and MC2. It is located near to the edge of this MC2 cloud, as you can see from the Gaia distance which you have calculated. And the distance of this Gaia 20 AE is around 3.2 kpc, as opposed to the Gaia as opposed to the MC2 molecular cloud, which is around 3.4 kpc. So we just started our observation of Gaia 20 AE after this Gaia photometric alert system issued an alert on this 28 August 2020 that this source has undergone an optical outburst of around 4.25 magnitude. So this is the so as this is, you can see by visually the magnitude change of this source, as this is the archival HDSS image in the upper panel, and bottom panel is the post outburst image as obtained from the 2-meter Himalayan Chandra telescope. So, and this is the log of our observation. We use the various international facilities for our observation, like the 2-meter Himalaya Chandra telescope, the 10-meter Hobe-Belly telescope. Then there was the 3.6 meter, there was the optical telescope, and 1.3 meter, there was the first optical telescope. So, and this is the historical light curve of Gaia. As you can see, it had a long quiescence, and then there is this outburst stage. So as next, I show you the zoomed version of this light curve. As you can see, this light curve of Gaia 20 is interesting in the sense that the rise rate is the fastest till date, as has been recorded in this category of sources, of around 0.1 magnitude per day, or around 3 magnitude per day. It rose very rapidly. So as opposed to the bona fide FUOs or XORs, which had a typical rise rate of around 0.15 magnitude per month or 1.1 magnitude per month, this recorded, this is the first source which recorded very fast rise rate. And also, but the decay rate of this source was that of the typical XOR type of sources like Xlupi of around 0.01 magnitude per day, or 0.1 magnitude or 0.3 magnitude per month. So this kind of difference hint at the different physical magnitude and triggering mechanisms which are causing the outbursts. So next, we performed the period analysis, found the calculated the periodicity of the source in the quiescent stage. We found that the source exhibited a period of around 2.1 day, which is typical of class 2 or 3 sources, normal class 2 or 3 kind of sources of YSOs. And then we performed the ACD evolution. In the left-hand panel, you can see the quiescent phase and the active phase ACDs. And in the right-hand side, we calculated the difference in the observed ACD with that of the line of sight extinction, both for normal extinction of 3.1 and also for the heavy extinction found in the star forming sites of around 5.5. As you can see clearly that the present brightening we cannot be explained based on the simple changing in the line of sight extinction. So we also perform this color evolution using the reddening invariant colors. The reddening invariant colors have a generic form, as you can see by the equation, and as it is a weighted mean of weighted difference of the two colors, it is invariant of the change in extinction. Any change in the color which is statistically significant of around 5 sigma can change us that the present change in the ACD is not due to the change in extinction, but due to change in other phenomena like accretion or like accretion, or the change in accretion. So as you can see from our monitoring, in the QVRI plots, the significance is more than 5 sigma, and we can clearly say that this present brightening is due to, from photometric analysis, is due to the variation in accretion rate of the source. Next, we obtained the spectra of our sources. We use the 2-meter HCT and the 10-meter HET telescope for obtaining our spectra. From the optical low resolution spectra, we can identify the H beta lines, iron 2 at 5018 angstrom, then the sodium D lines, and then the Fe2 line, H alpha line. We observed on the P Cygni profile in H alpha, and also we found these absorption features in potassium 7699 angstrom and oxygen 7773 angstrom, 7773 angstrom, and emission feature in the calcium triplet lines. So most of the lines in the optical are blue shifted and are observation features. However, the Tanspec spectra, which we obtained from 3.6 meter telescope, so that there is the carbon monoxide to bands at 2.29 micron and 2.3 microns are in emission. So these features, this state that the temperature inversion at that part of the disk disk, as opposed to the FEOs. The typical FEO source shows the absorption feature, whereas the XOR sources show the emission feature in these lines. Also, we found this interesting line at helium-1 at 10,830 angstrom, which was blue shifted, heavily blue shifted. This line acts as a proxy or tracer for the heavy in determining the shocked regions that are formed due to the enhanced accretion rate. So next slide, I will show you the evolution of the different spectral lines that we have found. As you can see here, the absorption features in the H beta sodium line and the P Cygni profile in H alpha and the other lines. And also you can clearly see the change in the helium 10830 line here that we observed during our in our monitoring period. Next, we also calculated the velocities of this blue shifted lines. These are the typical velocities are found in the FEO sources, and the typical error in this in the velocity is around minus per hour. So such large scatter is only we can be explained because of the high outflowing regime as happened due to the enhanced accretion rate. Next, we also calculated the radial velocity of Gaia from using these chromospheric lines of Fe and Ti. So using the radial velocity comes out to be around 35 km per second, which also which is similar to the molecular cloud velocity of MC2 of around 42 kilometers per second. From this, we can associate it that this cloud is associated, that this source is associated with the MC2 molecular cloud. So next is the high resolution spectral findings that we have obtained from the 10-meter telescope. We can see here the deep, the high resolution spectrum 10830 line as it extended from beyond minus 400 kilometer per second. From the 10 spec feature, we found that this helium 10830 line, the outflow velocity as traced by this line varied from around 593 to around 490 kilometer per second. Also, we found some weak emission features of these Paschen beta lines of hydrogen. These are the features which also acts as the faint accretion tracers. This, as we can see. And next up is the most important observation that we found for this kind of source is the complicated structure in the calcium triplet line in the high resolution spectroscopic feature. We see one red shifted absorption feature in this calcium triplet lines, which is the first time detection for this kind of sources. So this kind of sources detection for this kind of sources. This blue shifted, this red shifted emission is unlike that of the. Okay. So I'm in the last slide. So this can only be explained by saying that we are at some vantage point. We are looking through these accretion funnels that is coming from the base of this disk to the polar regions, as shown in the cartoon diagram alongside it, and these are the main findings of our sources. The outburst magnitude was around 4.25 magnitude in all the optical bands. It is the furthest discovered episodically accreting source till date, and the photometric decay rate is similar to the XOR sources, and it is a mix of the FEOR and XOR sources spectroscopically. And these are the classification. This is where the Gaia stands in comparison to the FEOR and the XOR sources, as you can see. So, and thank you.
Thanks a lot, Arpan, for the very nice talk. So we are open for one quick question. So anybody from online participants? Yeah, if not, so we will go ahead for our next speaker, Archana Soam from IA. She will be talking about on the collisional disalignment of dust grain in illuminated and shaded region of IC 63.
Thanks, Saurabh. I hope you can see my.
Yeah.
You can see my screen, right?
Yes.
Okay, I'm going to full screen mode. And okay, so in these 15 minutes, I'm going to talk about our recent work on.
Archana, you have 12 minutes.
12 minutes, okay. Work on that is collisional disalignment in a PDR IC63, which lies in Sharp +2 185 region. So this work was done with some of my collaborators. And outline of this talk will be, I'll give some introduction on PDRs and interstellar polarization. I'll tell about the motivations of this work. I'll tell about why we chose this region and what method we used and what were the findings, and little bit about the summary. So photo dissociation regions, they are always beautiful when you see the Hubble images. For example, these pillars of creation taken with Hubble Space Telescope, you can see these pillars of creation, and these shining fronts of these pillars are the locations where PDRs lie. So if you have a knowledge of ionization potentials of different atoms and dissociation potentials of different molecules, you can have an idea that where these molecules and atoms and ions are lying in the PDRs when the molecular cloud, pre-existing molecular cloud gets illuminated by high mass stars. And thanks to Lokesh's talk, he gave some idea on what these high mass stars do to their surroundings. So this is the very high resolution observation taken from ALMA towards Orion, and bar was seen in these observations, and it was first time resolved with different molecular tracers, and they could see the ionized gas, ionization front, and molecular gas shown here in green, blue, and red colors. But my motivation is not to show these colorful pictures. My motivation is to understand if we can use the polarization to test the theories of dust grain alignment in interstellar medium, and especially testing the disalignment of the dust grains. And I also want to test a hypothesis given by a study in 2009, which says that in one of the PDRs called IC63, there are 2 temperatures. So I want to test that hypothesis also by using my existing polarization measurements and also some line observations. So as I'm saying polarization, so polarization is the third leg in the toolkit of astronomers for astronomers. So it has the potential to understand the interstellar magnetic fields, and we are very, very well aware of these very beautiful blank images with interstellar magnetic fields. And we should know, before interpreting these magnetic fields, we should know that how the dust grains are aligned in the interstellar medium to understand the polarization. And a very well established and now lab tested theory about the interstellar polarization is the red alignment, which is the radiated torque alignment, where the anisotropic radiation has to move. So with a wavelength less than the size of the grain means asymmetric grains, and when it hits the interstellar radiation field, when it hits these asymmetric grains, it gets them spin, and because of the interstellar magnetic fields, they are aligned in such a fashion that we get a polarization component of the background starlight. I'm not going deep into the polarization mechanism here. So this is the region under investigation. This is IC63, IC59 reflection nebulae lying in Sharp +185 H2 region. This region is nearby at a 200 parsec distance, and the distance is of the gamma gas, the illuminating source in this region, to IC63 is around 1.5 parsec. So it is in very close vicinity to its ionizing source. So 2 tests, as I said, I'm going to do 2 tests using polarization measurements. One is to understand how the gas grain collisions can cause the drop in the polarization. Another is to check the 2 temperature hypothesis in IC63. So this is just a cartoon to understand that what happens to polarization if gas and dust grains collide with each other. For that, you have to have some knowledge on the equations developed by the theories on grain alignment, especially the red theory, where they consider that there are some enhancing mechanisms, grain alignment enhancing mechanisms, and some are damping mechanisms. I'm not going into the details of these equations. So by having the knowledge of these equations, by having the background knowledge on red alignment, we thought, okay, let's go to the second hypothesis. I'll go to the results, but before that, I'm just flashing these results here. In 2009, he gave a hypothesis that IC63 has two temperatures towards this gamma gas. So one is hotter temperature at a temperature of around 685 Kelvin, another is warmer at 100 Kelvin. And he found these results by using short wave spectrometer from Infrared Space Observatory. He was using pure molecular hydrogen lines from S0 to S5, and then he created this rotation diagram where you can see this these level populations with the energies. So this was the underlying hypothesis. It was not tested, but we want to test it using polarization. So what we had our well-sampled polarization measurements published in a few years ago from these observations were taken from AIMPOL, and we had magnetic field morphologies and polarization information, dust polarization information. And we also had some high resolution HCO plus J120 line emission taken from Karma towards this cloud. We did a deliberate stretching in this emission map just to see these clumpy structures of HCO plus. And you can see these red and blue dots here, which shows that there are, I'll show you, we tried to divide our sample into two populations, one population lying behind or in the shade of these clumps, and one population lying in front of the clumps, which is directly seeing the radiation from gamma gas. So these two things we had. So to understand this stretched image, we created a cartoon saying that, okay, this is the location of the gamma gas from, and this is the direction of the radiation coming from gamma gas, and we have this red and blue line of sites. So red are the population which is seeing this UV radiation, and blue are the population which are kind of in the shade of HCO plus clumps. So that might be in the cooler region, and red ones might be in the hotter region, but we want to prove it with the polarization. So what we did, we plotted delta P. Delta P is nothing but the difference between the all the P values we had in the line of sights, red and blue, and the P mean. So for now, just ignore the blue and red populations here. Just ignore that. Just see that how delta P is going with the HCO plus intensities. So this horizontal axis has HCO plus intensities, and vertical axis has delta P's. It seems that polarization is going down with the HCO plus intensities. So wherever the HCO plus intensity was high, there may be the gas and dust collisions were higher, and that's why the grains which were aligned were getting disaligned. I could use misaligned word here also, but people try to use disalign, and that's why the polarization efficiency was going down, and that was seen in our results. That polarization was going down towards the higher gas intensities because of the enhanced collisions. Now, let's now focus on these two populations, red population and blue population. So blue population was the population which is in the shade of the HCO plus clumps, and red population is the population which is hit directly by this ultraviolet radiation from the gamma gas. So what we see is that the blue population goes shallower, like the slope of the blue population is shallower compared to the steeper slope of the red population. And the temperature of this region, red population, was higher because it is directly hit by the radiation, and the blue population was little cooler. So even in our sample where we are just plotting delta P's with the gas intensities, we are seeing two different slopes, which is proving that, okay, there may be two temperature regions, and what Thi said was kind of correct. So we are kind of proving his hypothesis of two temperature regions in IC63 just by using polarization and gas intensities. So this was the first test done on any PDR which is nearby. But okay, so before going to the conclusions, what I'm going to emphasize here on is in the left-hand side, you can see his plot, which was 685 and 100 Kelvin. He was getting two slopes in his pure rotation molecular hydrogen observation lines, and we are getting two slopes in the drop in the polarization with the gas intensities. So we kind of tested his hypothesis. It was correct, but we are doing this. We are testing this hypothesis further by using high resolution molecular hydrogen, pure rotational molecular hydrogen observations from Sophia, and that paper was published a month ago. And there also we are seeing signatures of 2 or 3 temperatures because those are high resolution observations, and in the region which is directly hit by the radiation here, in that region we are seeing variations in the temperature and density, and that might be caused because of this high energy radiation. And after that, okay, I think I'm done. Okay. So these are the conclusions of this study, where I'm trying to say that polarization is decreased by the gas grain collisions, and it is consistent with the two temperature structures proposed structure of the IC63 nebula proposed by Thi et al. Also, one more thing to notice in this plot, there is a horizontal and vertical lines, dotted lines. So these lines correspond to this 0 value, and the line which is 3.5 hitting this 3.5. If you just extrapolate this red line to upward, so that is the density of the hotter region, beyond which the gas grain collisions will be effective, and the disalignment will be effective and polarization will start going down. But if you go to the cooler region, the bluer population, the densities are higher, and that is the density beyond which the gas grain collisions will be effective to disalign the grains and to further decrease the polarization. So this also goes in line with the temperatures, because in cooler temperatures, you have more densities. In hotter temperatures, you have less density, but you have more rate of collision, because rate of collision goes directly proportional to the square root of the temperature. So this is also a finding in our investigation. So that was another thing. Other is that higher temperature corresponds to the line of sights, which are directly hit by the radiation from the high energy source, and lower temperature population corresponds to the line of sights which are in the shade of the clumps. So this was just one test on one PDR, but the details of this work and all the calculations and the equations can be seen in our paper published in 2021. And this is the barcode you can scan for that. And this investigation we are extending to many PDRs, where we already have polarization observations either from near infrared, or from optical, and also we have line measurements. So one catch here is that why only Karma and why only HCO plus observations? We only had these observations available by the time we started this investigation, but in future we are going to extend it to the observations from GBT. We got CO high resolution observations and maybe some ALMA observations in other PDRs, because we want to test this hypothesis further in the higher density regions, because optical polarization was limited to very diffused parts. We were missing many line of sights. We had gas measurements, but we did not have polarization measurements. So we want to go to the higher density tracers in gas, and also high density polarization measurements, so that we can do this test better in other PDRs. So if you're interested, please feel free to contact and be a part of the investigation. Thank you.
Thanks a lot, Archana, for a very nice talk and giving in time. So one or two questions from audience, and from online participants. If you have any query, please type in the chat box. No, thanks, Archana, for the nice talk.
Thank you for this opportunity. Thank you.
So we'll go to next talk by Aritra Chakrabarty. So he will be talking about the characterization of atmospheres of exoplanets using the polarimetry. So Aritra, you can share your screen. Yes, we can view. Yeah, please go ahead.
It's visible, right?
So you have 12 minutes only.
Yeah, okay, thank you. Good evening, everyone. I'm Aritra Chakrabarty. I've just completed my PhD.
Can you speak a bit louder?
Is it not
Yeah.
louder? Is it okay now?
Yes.
Okay. Good evening, everyone. I am Aritra Chakrabarty, a PhD student. I mean, I've just completed my PhD from the Indian Institute of Astrophysics. So I'll be my topic up for this evening is on an interesting and emerging field in the exoplanet research, which is on characterization of atmospheres of the exoplanets using polarimetry. So first is the motivation behind this polarimetric study. So that is associated with the limitation of the existing techniques that we have in hand. So let's see what are the different existing techniques that we have for atmospheric characterization of the exoplanets. So the close-in planets, we have techniques like transit photometry and spectroscopy, then photometry and spectroscopy, the secondary eclipse. Then there are phase curves, that is reflection and thermal emission phase curves in the visible wavelength and in the infrared wavelength respectively. And in future, we'll be having phase-dependent spectroscopy with using GWST or HABEX, etc. And then for the directly imaged planets, we had direct photometry, or you can in future we are aiming at direct spectroscopy of this directly imaged planets. Now, the problem is, so what are the limitations that we have with these techniques? For the close-in planets, the most popular techniques are transit-based and radial velocity-based studies, and they require that the orbital inclinations are highly edge-on, that is 90 degree, close to 90 degree. I mean, if it is away from 90 degree, then it's not possible. And then also we find that while retrieving the properties using a retrieval technique from the spectral data, we find either high degeneracy among the estimated parameters, or we find high uncertainties in the parameters because of the error bar, high error bar in the data. And also we find incomplete information about clouds, because clouds are ubiquitous in the atmospheres of the exoplanets. And they I mean, they affect almost every photometric and spectroscopy observation. And but we cannot interpret them with the because we cannot directly detect the nature of the clouds with the spectroscopic and photometric techniques. And for the directly imaged planets, the problem is that we do not have any direct estimate of mass or size. So we have to rely on the evolution model to interpret or to estimate the properties like surface gravity, effective temperature, etc., mass, etc., from direct spectroscopic observations. And these highly depend on the initial conditions that we are assuming. And again, evolution models are also highly reliant on the cloud models. So again, cloud information is essential, and there is no way with the existing techniques that we can tell what is the tilt of the spin axis of a planet. I mean, you can maximum at most we can say whether it's prograde or retrograde spin, but we cannot specify the tilt of the spin axis. So herein comes polarimetry. What are the information that we get are like polarimetry observation. First of all, it's an additional information. So it complements the existing photometric and spectroscopic techniques. It can in future, and then tell us more detail about the properties like surface gravity or presence of atomic absorbers. So we can basically reduce the degeneracy. And also we get orthogonal information about the clouds. For example, we get both the cloud depth or height and as well as the size of the cloud particulates. So, and then polarimetric observations, again, since it's an additional information, it can be used to verify the evolution models as well as the cloud models for the directly imaged planets. The polarization is not something extremely, absolutely new. We have seen that there are the polarization reports for brown dwarfs already out there, and also for solar system planets. So that's why we expect the exoplanets to be also polarized, the light from the exoplanets to be polarized. And so there are some recent observations which have been only able to set upper limit on the observable detectable polarization of such planets, like using instruments like SPHERE, GPI, or Planet Pol, etc. So, and what is the need for polarization models is that when we have this data in future, so we need to ready our models prior so that we can interpret those polarimetric observations, because they are strictly model dependent, the interpretation is. But the present urge is that these models will play a useful role in guiding the design and the roadmaps of the parameters of the upcoming instruments, of the upcoming missions like HABEX or TMT, models of Duvois, etc. So I'll just briefly describe what polarization is and how it originates from scattering of light in the atmosphere. So basically, we are aware of the term Stokes vector, that is IQUV, where I is the total intensity, Q and U are the linear polarizations, and V is the circular polarization. It's set to 0 because because the effect of scattering on V is ignorable. And so we will be focusing on linear polarization. So the total degree of linear polarization is Q square plus U square root under by I. So what happens when light is scattered by a molecule or an atom or a cloud particulate? Then it gets polarized depending on the angle of scattering, and it's represented by this phase matrix term, which depends on the nature of scattering. That is the scatterer. So this is how it looks. If you could resolve the planet's disk, as we've seen in case of sun as well, so we can see the alternate positive and negative polarizations patterns over the disk. And so but since we cannot resolve, actually, we see the total polarization coming out of the planet, then it gets 0 if the disk is symmetrical. But if by some means there is some asymmetry in the disk, then the net disk integrated polarization is non-zero, which is where we are interested in. So that means there is some source of asymmetry which will give out the polarization, and that will give out the information of the planet as well. So there are different sources of asymmetry. One is the reflected light from the asymmetrically illuminated planets, like phase-dependent asymmetry, day-night asymmetry. And then there is effect of, I mean, the thermal emission from the self-luminous giant planets or the brown dwarfs can be polarized because of like the rotation induced oblateness, because they are highly rotating if they are young. And then also there will be non-uniform banded cloud patterns can cause polarization, and there are many other reasons. So I'll be focusing on these two reasons particularly. So I'll try to model them, identify the target is to identify the source of polarization and then model it accordingly using the vector radiative transfer equations. So the first is the polarization from reflecting giant planets. So for that, you assume a planet at an orbital, at an arbitrary orbital inclination, say I, and then we can calculate the effective phase angle depending on the phase position on the orbit. And then this is the front view of the disk. This is a partially illuminated disk, and the red line shows the day-night terminator. And then so we segregate the entire disk into a grid of mu and phi, where it's a polar angle, I mean cosine of the polar angle, and phi is the azimuthal angle. And then this is work is the part of our 2021 APJ, in the 2021 work in APJ. Then this is the vector radiative transfer model that consists of the multiple scattering term and the single scattering term. So the trivial part is the calculation of the phase matrix, especially in this case because it's not axisymmetric, it's actually highly asymmetric, and so this is basically a multi-dimensional array that needs to be taken care of. So we assume Rayleigh phase matrix for the cloud-free atmosphere, and me or Heinier-Ginstein Rayleigh phase matrix for the clouds. So this one shows that as the single scattering albedo increases, the reflectivity or the total.
You have 3 more minutes.
Right. Okay. Albedo increases and the polarization drops. So these are two representative cases. One is inclination angle with 90 degree, and another is for inclination angle of 60 degree. So you can see this cartoon shows the polarization map across the disk for as a function of phase and for two different inclination angles. And when you integrate them, this is how the polarization looks. We can expect about maximum of 40 to 45% of polarization depending on the inclination angle, and also if we can resolve the planet separate out from the host star. But that is not the case in case of the closing planets, because we cannot separate out the host star. So host star total light has to be considered, which we assume to be unpolarized. Then the left-hand term is what we observe, is the observable flux ratio and the observable polarization, which is less than the actual disk polarization. So this one shows the predicted polarization for the planet HG 189733b. You can expect a maximum of 20 or 22 ppm polarization, and for the including clouds, it's even less. And also the presence of atomic absorbers like sodium potassium also affects it. So it's a way to detect whether sodium potassium are present or not. So now, but even though it's in the ppm level, but it's in the sensitivity level of the instruments like HIPI, Polish, or Planet Pole, etc. So in future you might have an observation. Then there's the giant deeply imaged planets. So there's a rotation-induced oblateness. I've shown this plot of oblateness as a function of the equatorial speed, and then depending on the spin axis tilt, the effect of asymmetry is prevalent. So for 0 degree, that is for polar view, you can see the asymmetry is almost minimum, almost zero. But for equatorial view, that is for 90 degree, the asymmetry is maximum. So this is our recent work in 2022 in the APJ. So for the 90 degree case, so the total atmosphere can be considered as an oblate spheroid shell, where the depth in the equator is more than the depth in the pole. So this one shows the polarization pattern and the intensity pattern across the disk for three different axial tilt. You can see for 90 degree, the polarization across the azimuthal direction is, it shows maximum asymmetry. That's why when you integrate over the disk, it is non-zero. So this is a case for 5-hour rotation period. And you can clearly see that the limb darkening of the intensity and limb brightening of the polarization across the disk. So this is our model prediction for spectropolarimetric model. The left-hand side is the spectropolarimetric model as a function of effective temperature and surface gravity. But with the present technology, because of the limited signal, we are only attempting band average polarimetric model, band average polarimetry using instruments like sphere or GPI. So the right-hand side, this is a corresponding model in different bands of sphere. You can expect a maximum of 0.4 or 0.16, maximum 0.4% polarization from using sphere from the directly imaged planets. And this is a particular for model for beta peak B, which has been already attempted. Its rotation speed is already V sin I. That is, V sin I is recorded by Stenel et al. 2014, but we don't have the information of I. So this one shows the possible range of I that we can have when we have the actual polarimetric observation of this planet. So anyway, to summarize the entire talk, the observation of polarization of close-in planets is very difficult. Presence of clouds significantly dictates it, but these instruments like Planet Pole, Polish, etc., has sensitivity level in the order of ppm, so we might be able to detect them. But what we are presently working at is observation of polarized thermal emission from the directly imaged planets, which will be possible, which is already possible, and will be possible using instruments like Sphere or GPI, and in future with like Roman Space Telescope, HABEX, or TMT models, etc., using the coronagraphy instruments. And the same coronagraphic instruments can also be used, but are being planned to be used for detecting the polarization of the reflected light of such planets, directly reflecting planets. So those are like at the distance of 1 or 2 AU. So this is where our models play a major role for designing and also for predicting the polarization. And so we will be upgrading our models further by including effects of like inhomogeneous patchy clouds, because as I said, this is a common phenomenon in brown dwarfs as well as planets. So we'll be working on that. Thank you so much.
Thanks, Aritra, for the very nice talk.
Thank you.
We have time for a couple of queries from audience and from online participants. And if you have any query, please type in the chat box. Okay, so thanks a lot, Aritra. So you can answer this. Yeah. So now we'll go to the last talk in this session from Ruchi Pandey. So we'll be talking about photoionization of modeling of the dusky nova V1280 Scorpii. So Ruchi, you have only 12 minutes.
PDF. Share.
Hello everyone, I'm Ruchi Pandey and I'm a PhD student working at the Arpan Ghosh National Center for Basic Sciences. And today I'll be talking about the photoionization modeling of dusty nova V1280 Scorpio. So I'm going to start by giving a brief introduction of the subject, and then I'll talk about the dust formation process in nova and what are our attempts to study this process, and then I'll end with the summary. So let's start by giving a brief introduction of the subject. What are novae? Novae belongs to a class of cataclysmic variables. These cataclysmic variables are interacting binary star systems. As you can see here in the schematic diagram, these binary systems has a white dwarf primary and a secondary is a main sequence companion star. Now, because of the high surface gravity of white dwarf, the hydrogen-rich matter from the companion fills its Roche lobe and forms an accretion disk around a white dwarf. Now, this over a period of time, the accreted matter forms a layer of fuel on the surface of a white dwarf, and at the bottom layer of this accreted layer, the temperature and pressure increases. Now, at critical temperature and pressure, this hydrogen burning sets, which further triggers the thermonuclear runaway. Now, this thermonuclear runaway reactions releases the tremendous amount of energy. Now, this tremendous amount of energy which is released distorts the accretion disk and the matter ejected out in the space. Now, this explosion on the surface of a white dwarf is known as nova outburst. So nova outburst is observed as a sudden increase in the brightness of a star, which follows by a decline. Now, here a figure which illustrates the typical brightening of a nova. Before outburst, we see a very very less brightness of a star. Just after an outburst, the brightness of nova, it increases. Now, these are the typical characteristics of a nova system. It's in a binary star system, and the outburst energy is around 10 to the power 45 ergs. And the outburst, in the outburst, the mass ejected is around 10 to the power minus 4 to 10 to the power minus 5 solar mass, and the ejected, the ejecta usually have enhanced, metals usually enhanced over their cosmic values by 10 to 100 times. And in the single outburst, we also see grains and different types of molecules. Now, on the basis of outbursts, we further classify these systems into 3 different types. Those systems which have showed only 1 recorded outburst are known as classical novae, and the systems with more than 1 recorded outburst are known as recurrent novae. Now, we have a third system which are known as dwarf novae. Dwarf novae also shows multiple eruptions, but the main difference between classical, recurrent, and dwarf is that the outbursts in classical and recurrent are triggered by thermonuclear runaway, but in dwarf nova, the outburst is caused by the increase in the luminosity. In this presentation, I'm going to talk about the classical novae. Now, this is a typical light curve of a classical nova. We have a pre-nova stage, then during outburst, we see an initial rise, and then at outburst, it reaches the maximum brightness, and then after that, it declines. Now, this declination from the maximum brightness further is not same for the different novae. It varies for different novae, and we can use this declination to classify novae in different speed classes. Now, in year 1955, a parameter T2 was defined, which is the number of days a nova took to fall 2 magnitudes from the maximum brightness to classify novae from very fast to very slow novae. Now, after outburst, novae passes to a different phases. And one of the interesting phase is the dust formation phase. Why it's interesting? Because only a small fraction of all observed novae has formed this dust, around 20 to 25%. And this hypothesis that these systems are forming dust was first suggested by McLaughlin in the year 1935. And this hypothesis was confirmed by from the advantage in the infrared observations in year 1970. So here you can see a light curve of a dust forming nova DQ here. As you can see here, there is a sudden dip observed in the visual light curve. So using this light curve, there was a hypothesis that this dip we are observing because the dust is forming in this system and this dust is obscuring the light. Now, these systems can be a perfect laboratories to study the astrophysical dust. Why? Because the observations have shown that the dust is forming in these systems in a very short period of time, that is months, if you compare it to ISM dust. And in a single outburst, they show all possible kind of astrophysical dust. And again, we see a signature of both simultaneous carbon and oxygen grains in a single outburst. And the grain size are also different when we compare it to the ISM. But how these dusts are forming in these hostile environments is still unknown. It has been an open question for decades. So these are the IR signatures of dust formation in novae. As I've shown in the previous slide, we observe a dip in a visible light curve. Simultaneously, we see a rise in the IR flux as the absorbed energy is irradiated in infrared. Now, this leads to some open question in here. Why only some novae are forming dust and others do not? And how the dust is forming in these hostile environments? What are the physical conditions which are required for the formation of dust? And is there any effect of metal abundance of this on the grain formations? So here our aim is to study this dust formation process in novae. And we try to understand the variation of different physical and chemical parameters associated with the formation of dust in novae. So as a part of this work, we have studied a dust forming nova candidate V1280 Scorpio. It was observed in year 2007, and the magnitude as the maximum was 3.79. The interesting thing about this nova is that on about 23 days after the outburst, the nova has started showing the signature of dust, and that can be clearly visible. By looking at the light curve. Just after this 23 days, we see a decline in the visible light curve and simultaneously a rise in JHK band. So these are the, so for this purpose, we have used published NIR and optical data. This is the data of duality Scorpio for pre-dust phase in NIR and optical. And these are the data for the post-dust phase. As you can clearly see, after the dust formation, we see a rise in the IR continuum. So to study this problem, we approach this problem phenomenologically. We constructed a phenomenological model by using a photoionization code, Cloudy. So Cloudy here, it uses a certain sets of input parameters, which used to specify the initial physical conditions of the source and the ejected cell. These input parameters could be the temperature and luminosity of the central ionizing source, and the density and the inner and outer radius of the ejector. Now, this Cloudy takes these parameters and solves the equations of thermal and statistical equilibrium and predicts the output flux, and that we can compare with the observed flux. So this is the model description of our phenomenology. We assume that the central white dwarf, black body for the central white dwarf with the parameter T, temperature and luminosity, and it is surrounded by a spherical symmetric geometry. And
you are going to.
Okay, so we calculated. We assume that the hydrogen density follows with the varies with radius with this formula, and then in this ejector we set the abundances with respect to their solar value, and then we scale them. So this is our initial attempt to model. First, we considered a single density region, but it didn't work out. Then we have to consider we have to add a second density component. Means first we added a region. First, we considered a region with the low hydrogen density. That region successfully generated this lines with high ionization potentials. But in order to generate the lines of low ionization potential that we see in the observed spectra, we had to add a density of high hydrogen density, and we call it. And this is the two-component model. So these are the results. The red ones are the model predicted spectrum, and black ones are the observed spectra for pre-dust phase. Now for post-dust phase, we find then we had to consider the effect of grains in the model. So when we added the dust grains in the inner region of our phenomenology, we find out that the temperature of the inner region exceeds the sublimation temperature of the grains, and we cannot add the grains there. So what we did, we checked at which region we can add the grains. So we find out that when the ejector temperature reaches around 2000 Kelvin, the hydrogen density of that region is sufficiently high. That is around 10 to the power 8.5 per centimeter cube, and grains can survive there. So we added we updated this phenomenology, and we added another shell in just out in the at the outer region of the clump part. That is the region of high hydrogen density, and we save the transmitted continuum from the first shell, and we use it as an input for the second shell. And then we added the resulted spectrum from both parts. So these are here we have successfully modeled the rise in the continuum. So these many lines in simultaneously optical JHK band we have used for this phenomenology. We have studied the 4 epochs. These are the Cloudy best fit model predictions we get. So to summarize, we find out that we need a very high hydrogen density to generate the spectra in this case, and thus condenses in the clump component. Clump component means the region which has a high hydrogen density at the temperature around 2000 Kelvin, and that region is around 10 to the power 15 centimeter far away from the central ionizing white dwarf. And the density of those regions at the ejecta is around 10 to the power 8 per centimeter cube. And we also find that the ejecta is the metallicity of this ejecta is enhanced. We found a very high abundance for nitrogen, around 250 times of its solar value. And we also find out that to generate the spectra properly, we required a small mixture of small amorphous carbon dust grains and a large astrophysical dust to generate the spectra. So thank you for your attention.
Thanks, Ruchi, for the very nice talk. So we have time for a couple of questions.
Nice talk, Ruchi. I just want to know one thing, maybe not directly related to work, but you spoke about the enrichment of ISM using NOVA. So I just wanted to know basically how is this enrichment compared to we see in kind of type 1A supernova, and also when did it happen in the epoch? I mean, when did the first novas occur? Do you have any information on that?
Enrichment in ISM, I don't understand.
I think in one of your slides you showed, right? If you go back, starting slides somewhere, or maybe I misunderstood. Can you just
Okay, so I compared it ISM. Okay, so I said that these grain formations, they are forming in a very short period of time. Like-
can you just go back to 2 more slides? I think it was in your beginning slide somewhere. Somewhere, yeah. Ejector composition. I just didn't understand that part. I thought you were talking about enrichment. Like that. Can you just? I mean, can you explain that part, please?
This here?
Yeah, the last point that you were saying, ejector composition.
Yeah, the abundance that we observe, they are usually enhanced over their cosmic values. I mean, we can observe around these metals from 10 to 100 times of their solar value, and they are consistent with the previous findings also.
Okay, we can discuss this
Yeah.
later.
Yeah, so any query from online participants? Yeah.
Hi Ruchi, I just want to ask, what is the role of magnetic field? Magnetic field of white dwarf in accreting matter from secondary to primary.
These are non-magnetic white
Yeah,
dwarfs.
but like they have magnetic field less than 10 to the power 5 gauss, I guess.
So we didn't consider any role of magnetic field.
Okay, so yeah, one more.
Hi, good talk. So I have one question about the dust formation.
Okay.
So you said about 10⁸ hydrogen density, the last slide.
Yeah.
So you say only 25% of the Norway have this dust formation.
Yeah, very small.
So what do you think the column density is it a parameter that is deciding will it form dust or not?
I mean, there are several approaches. It's still it's still an unknown question.
So because you did a model,
Yeah.
so you might have.
So we just wanted to
Treat the
see what are the
values
physical, like how these physical parameters and these chemical parameters, they are just, I mean, how these are, they are varying just before and after the dust formations. And we find out that like we require not like high density, sufficiently high density, around 10 to the power 8.5 this density to support the dust formation in these cases. And dust are forming at a very far distance from the central white dwarf, around 10 to the power 15 to 16 centimeter away from the white dwarf.
Yeah, any queries from online participants? There is one chat. Why is from Jeevan Pandey? Why did not you consider the role of magnetic field? So in your calculations, you did not consider the magnetic field. Is there any specific reason?
I mean, I haven't seen a lot of discussion on magnetic field in this dust formation cases. Like, so I mean,
yeah. Okay. Thanks a lot, Ruchi. And by this, we are on the end of this session. So I thanks both online and offline participants for listening these talks. Thanks.